4F, graphing polynomials. So today we're learning about graphing polynomials of higher degrees. We're going to be recognizing graphical features of various polynomials, recognize points of inflections and turning points, and graph polynomials of higher degrees. Particularly, we're looking at quartics. So, uh, hopefully, in this exercise, you'll actually start to see some sort of a pattern emerging. So, we always have a base graph or a base function that looks like this over here. Again, it looks like your turning point form, it looks like your inflection form. The only difference is the power. So, our key point here, as it has been with all of our past functions, is h and k. With a quartic and with any function that is to the power, to an even power, it is always going to be a turning point. So in this case, it is a quartic with a turning point at h and k. It's very similar to the shape of y equals x squared, except of course, because it's to the power of 4, it grows a little bit differently. So if you kind of think about our function x squared, that's just going to look like this. That's just our basic parabola. But really, so the power of 4 is just x squared and then square it again. So what ends up happening is that for all numbers that are whole numbers, as not necessarily whole numbers, but that numbers larger than 1, when you put that to a power, it grows even faster. So think of, for example, 2 to the power of 2 is 4 compared to 2 to the power of 4 is 16. So all of the numbers that are greater than 1 actually create a steeper arm. Now, if we think about fractions, it's going to act in the opposite way. So a half squared is a quarter compared to a half to the power of 4 is 1 on 16. So what ends up happening with a quartic is that we have a flatter bottom. And that actually happens with all graphs, no matter what the power is, if it's even. So to the power of 6, 8, and so on, all of them will have steeper arms and flatter bottoms. And that's essentially what the general shape of a higher polynomial for a quartic or an even powered graph. The same is going to apply for anything that is odd power. So we know that a cubic looks like this. And then if we have anything to an even, to a odd power, we have the same idea, steeper arms, flatter bottom. And it's going to look something like that. Okay, so let's focus on quartics because that's the main thing about this exercise. So as we know, if the graph is positive, it's going to be facing upwards. So it's going to look like that. However, if it's negative, it'll be looking like that. The axis of symmetry equation is that x equals h, very similar to quadratics. And there could be either 0, 1, or 2 x-intercepts based on the actual form that we're given. So let's talk about all of the different forms that we have for quartics. So obviously we've just seen there the turning point form. That one's very straightforward. It just looks like a parabola, just flatter bottom, steeper arms. But we can also have a form that looks like this. That's where we have 4 distinct x-intercepts. And so it ends up forming a W shape. So that's for a positive graph. And then for a negative, it'll just be an upside down W or an M. The easiest way to remember which way it goes is just as simply as if it's a positive, then it's kind of like a parabola always looks like that, and it's just got some extra curves. Where if it's negative, parabola would look like this, but it has extra curves. Now, the same rules apply if our factors are repeated. So, for example, if I have a squared factor, that's going to become a turning point at that particular value of a. I can have 2 turning points in my graph, and I can even have a point of inflection. So I'll show you what all of these situations look like in a second, but you just need to think of them as generic ideas. Every time you have a squared, it'll be a turning point. Every time you have a cubed, it'll be a point of inflection. You can, for higher powers, even have to the powers of 4, 5, whatever. It just acts like how the normal base graph will act at that particular point. Okay, so let's go through all of them. The first one is our x to the power of 4. So as we said, we've got deep arms, flat bottom, and back up. So it'll kind of just look something like this. Okay, in general, we have the key points at H and K. So this one's probably not the best example. It's sort of centered at 0, 0, although not quite symmetrical, but the idea is that probably the turning point's around there. It's been shifted left or right. Now, this particular function is a quartic because the total is to the power of 4. So you can see one factor has to the power of 3, the other one to the power of 1. However, this one is going to be a point of inflection. So at the value of a, it is going to inflect, or rather, it's a positive graph, it'll do this, inflect, come down, and then it'll cut at B. Okay, so it'll look something like that. So that's just an example of what I've just drawn. Now with here, you can see that I've got both factors are to the power of 2, so both of them are going to be turning points. So it'll just look something like that. So a W that sits on the graph. This one has one turning point, and the other ones are just to the power of 1. So it'll kind of look like this. And then for the other two intercepts, it'll just cut right through the graph. So it'll look something like that. And then, of course, for this one, all of them are to the power of 1. So to the power of 1, think of it like a linear function. It just cuts right through the axis. So it'll look something like that. So you really just need to be able to look at a graph and be able to determine what it is going to look like. Now, we're going to go on with this example. Example 22, it says sketch this particular graph and hence determine graphically the number of solutions to this particular equation. So there's two parts of this question. I'm just going to focus first on this idea of sketching. So I want to sketch this graph. It's not in factorized form, so it's not that easy to be able to tell if there's turning points or anything like that. And we wanted to give you this example because it's actually very different to all the other ones. The other ones hopefully are very straightforward. You just chuck on the x-intercepts, and then if it's a turning point or just cuts, you can draw straight through. This one requires a different form of factorization. Now, of course, you can go ahead and long divide, but we all know that's quite a long process, so we want to try to avoid that if we can. There's something very special about this equation. Hopefully, you can recognize that the powers here are 4, 2, 1, and it kind of looks like a quadratic, but not quite. So there's a bit of a trick here where we can actually let a equal to x squared. And if you kind of think about it, this graph here, or this function, it's kind of like this. I can write that as x squared to the power of 2 plus 8, and then x squared minus 7. So wherever I see an x squared, I can actually just substitute an a. Now the reason I do that is look how much nicer this is now going to look. Now I've just got a very simple quadratic that I can easily factorize. Now, in order to factorize this or to solve this, I can make this equal to 0 to solve, and I can just divide everything through by -1. That'll just make my life a little bit easier. So what I'm looking for here are two numbers that will multiply to give me +7 and add to give me -8. That will, of course, just be -7 and -1. And when I work this out, that'll be 7 and 1. Now, of course, we're not solving for a, we are solving for x. So at this point, we can go back and substitute in the a is equal to x squared. So that means x squared is equal to 7, x squared is equal to 1. Therefore, x will equal to plus minus root 7, and x will equal to plus minus 1. So that is going to be all of my factors. Now, I'm going to go ahead and start to graph this function. So it looks like it's going to be quite a symmetrical graph. One thing to note, of course, it is a negative, so it's going to be an upside down W. It's going to look like that. We're going to have an x-intercept at negative root 7, -1, 1, and positive root 7. So we'll see how nicely I can draw this as symmetrically as possible. There we go, that'll do. So we can just quickly label all of our points here. And sorry, that should be a root 7 there. And we also need our y-intercept, of course. So if we have a look at the equation, when x is equal to 0, y will equal to -7. Okay, so that there is my equation. Now the next part says, hence determine graphically the number of solutions to this. We can kind of just sort of look at the function and be able to tell or see what's going on. So the first thing I can tell is that all of the signs are different. They've been swapped. So what's happened is I've multiplied everything by -1, or rather divided by. So that will indicate that there's a reflection in the x-axis. Now, if there was a reflection in the x-axis, so I'm just going to draw what that would look like with this color in the dotted line, I would be up here. This number here would be +7. And then what that's telling me is that instead of being at, so if I had multiplied everything by a negative, I'd be at x4 minus 8x squared plus 7. And then instead of +7, I want it to be a +3. So what that's telling me is I'm going to drop down my entire function by 4. So instead of that being 7, If we drop that by 4, I should end up at 3. So it'll look like that. So because this is still above the axis, I can still see that I should have 4 solutions. If, of course, it drops further down, then I would have only 2 solutions, which would be the ones on the outside. So that's what this question is referring to. Can you kind of tell what transformations have happened and what the graph is going to look like? So that dotted line there is just for this function. All right, that's the end of exercise 4F. You can go ahead and start graphing some quartics.